This video works through slides 14 to 23 of the Describing Numerical Displays PowerPoint posted on your course calendar. When we describe distributions, we describe their shape, center, and spread. Because this video focuses on spread, I want to take a moment to explain why we mention spread in the first place. Spread is related to variability, or how different the values of a variable can be from one another, or how different data values are from one another in a larger data set. Measures of center alone can be misleading. We've talked about how the mean can be skewed due to outliers, but even if there aren't outliers, even in a symmetric distribution, a measure of center might not tell us the entire story when we're looking at a data set. For example, if you had a major surgery and you were needing to take painkillers, you wouldn't want a drug company that produced the average correct concentration of an active ingredient for your pain pills. Just producing the average could be dangerous. That could mean that some of the pills don't contain much of the active ingredient while others contain too much, as long as they all averaged out together. So spread kind of addresses consistency, so to speak, in whatever it is the data represents. The measure of spread that you are probably already familiar with is the range. It's the simplest way to measure spread. The range specifically takes the largest value or the maximum of a data set and subtracts the smallest value. The range is one specific number, not simply stating the smallest and largest values. So if you had a data set where the minimum value was 2 and the maximum value was 10, you need to report the range as 8. You don't want to say the range goes from 2 to 10. That's a very common mistake. As we talked about the mean in class being not resistant to outliers, it should follow that the range is not resistant to outliers or unusual values as well. If there's one value that's much larger than the rest, the range can be kind of a misleading measure of spread, as the mean can sometimes be a misleading measure of center. Another measure of spread is called the interquartile range, or the IQR for short. I'm just going to mention what it is here, and we'll discuss it more in class when we go over box plots. But to give you the definition, the interquartile range is the range of the middle 50% of your data. So it takes the third quartile and subtracts the first quartile. Your calculator gives you these values when you calculate the 1-bar stats, as we did in class. You put numbers into a list, you tell your calculator 1-bar stats, it comes up with the mean, the sum of the values, the number of values, the median. These values show up there as well, so I'll make sure we highlight those in class when we get around to talking about box plots. What's nice about the interquartile range is that it's not impacted by outliers, and so we do consider this to be a resistant measure of spread. The most popular measure of spread, and the one that we will use most often in AP statistics, is called the standard deviation. This is a way of looking at how far observations or individual data points are from the mean and kind of taking all of those deviations into account. The formula is a little complicated. It is derived from something called variance, which is another measure of spread. It's just not as commonly used. And the standard deviation should only be used when the mean is an appropriate measure of center. We talked about how the mean is not a resistant measure of center. Similarly, standard deviation is not a resistant measure of spread. S is the variable that we're going to use for standard deviation, a lowercase s. And if we were to have all data values that are the same as one another, so maybe a list of values 4, 4, 4, and 4, that would mean that the standard deviation is 0, because the values don't deviate from the mean at all. The mean would be 4 if all of the values are 4. Otherwise, so what will be more typically the case is that S is always positive. It's going to be a number greater than 0. This slide shows us the equation for variance, so we're still not quite at standard deviation yet. Let's break down the symbols here to talk about what exactly it's doing. So we have our individual x values, so every single data point is going to then, we're going to subtract from each of those values the mean. So the difference between the mean and the individual data points. We're going to take that difference and square it. Part of the reason we square it is so that those values all become positive. Another is so that we can kind of exaggerate larger differences. We'll take the sum of all of those squared deviations from the mean, and then we're kind of dividing by the number of things. We're dividing by n minus 1 instead of n, which is why up here it says it's the almost average of the squares of the differences of each observation from the mean of the entire data set. So variance is s squared. It is the square of the standard deviation. The standard deviation then just takes the square root of that entire quantity that we just talked through. While we'll use standard deviation more often in our calculations, it's not completely unlikely that you would be asked to find the variance of a specific value. Standard deviation shows up in your 1-var stats, so if you were asked to find the variance, you would just square the value that shows up there. This standard deviation formula is something that is given to you on a formula sheet on the AP Stats exam, but it's not something that you'll actually apply. It's more so just a formula that you need to understand kind of what it's doing so that we can talk about how a standard deviation might behave if we were to manipulate a certain data set. So I don't want you to be too intimidated by the formula since you won't have to necessarily use it, but I do want you to try to start to wrap your head around the pieces of it. I've taken this paragraph from page 85 of your textbook. I'd like you to go ahead and pause the video so that you have a chance to read it. It's just trying to explain again what standard deviation and variance does. Pay special attention to not just the bolded text, but also that last sentence. There are two types of standard deviation that the 1-var stat function on your calculator will give you. It gives you a standard deviation to describe a population, as well as a standard deviation to describe a sample. There are just minor differences in their formulas. The first thing I would like you to notice is that the symbol we use for each is different, and this is, again, consistent with what's on your calculator. This first guy here is a lowercase sigma, and then we've already mentioned that S is used for standard deviation. I'm going to just put a star next to this one that describes the sample because it really is the version of the standard deviation that we will use most often. To give you a little bit of information of why there's a difference between these two, if we have information about an entire population, then, so let's say we wanted to look at the average height of BHHS students, and we had the heights available of everyone in the school. We would use this top formula here for their standard deviation. The only difference between the formulas themselves is that we multiply by 1 over n in the population formula and 1 over n minus 1 in the sample formula. So again, if we knew the heights of everyone in the school, we could find the direct average of the sum of the squares, and we'd be able to report that as an accurate standard deviation. But if we took a sample of students, and it should be a random sample of students to get kind of a good cross-section of the school, we would multiply by 1 over n minus 1 instead of 1 minus n, so that we get a bit of an overestimate of the average of the squared deviations about the mean. S will always be a larger number than sigma, again, so that it's kind of an overestimate and it accounts for some of the sampling variability that occurs whenever we are looking at just a snippet of our population of interest instead of the entire group. And this is a concept that we will revisit if it doesn't make perfect sense at the moment. So to wrap things up here, we know that we need to talk about the shape, center, and spread of a numerical distribution if we're trying to give a complete description. Choosing a measure of center and spread rests solely on what shape did you determine the distribution to be in the first place. If we have a skewed distribution, the median is the most appropriate measure of center to use, and then the range or IQR would be the most appropriate measure of spread. Choosing between these two might depend on whether or not you have some unusual values. On the other hand, if we have a symmetric distribution, we'll use the mean as a measure of center and the standard deviation, specifically usually S, since we're working with samples, in order to describe the spread for those distributions. Now, my disclaimer is that there are always exceptions to this general rule, especially if there are outliers present. So those will require a more detailed discussion when we get around to talking about the mathematical definition of an outlier, and then another exception comes up with box plots just because of how they're constructed. So more to come on that in the future.